Hello, my screen visible. Hello, hello. Am I audible? Good evening, Sumit. Am I audible? Okay. So last class we started with machine learning, and we progressed it machine learning is basically the task of guessing if given x and y pairs, and we move forward with it, and we sort of tried predicting these functions, and we saw that the function is very complex, it's harder to predict, but given x and y pairs, if a machine learning model can predict it very um, nicely. So then we move to terminologies of the ML, like where we started with features. What are the features and what are the labels that we have? And then we defined something called as dataset, which is a collection of all these features and labels. Then we used some notation here, and in this notation, like we sort of demonstrated that the features that are demonstrated like this, and these are the labels, and if we combine this will be the datasets. And so the fx is the target function which we are trying to learn basically. Then we move to the different tasks of machine learning, like classification and regression. So in the classification, we sort of classify things into different categories, and in the regression, we basically predict certain value. And so then I gave this uh, home price example, and for classification, I gave this cat and dog classification example, and then I move to how we will classify an image, and how we are passing all those values to our model, and how these images work, and what are these the components that the image have, like RGB values, pixels, and all these things. And yes, so I guess till this we have done our work. So is everything like clear to all the people? I guess how many people are there? 5 people are there. So for the people who joined last class, is this clear? Like, is this make sense to you? Like, could you remember what was done? Hello. Mhm. Hello. Yes, can we get last class recording? So actually the thing is that when when they like sort of started asking so in this they yeah, in this course they said that they shared with us a Excel sheet, and in the Excel sheet they asked to like upload the video link there. So we thought that they will share the link, but I don't know why they haven't shared it yet. But I will share it with you right now. You have to train, so then you can go for just. You can go back and if you want, you can look into the lectures once again. So this is the link that I shared in the chat. You guys can go. Actually, this is the channel I am like where I am uploading the video. So basically, I had to do a new channel to upload all these videos, but I sort of so I had a channel where I had just one video. So, but I couldn't like upload more after that. So I started uploading the videos in this channel itself. You can what you can do is that you can just subscribe to this channel, so that you can get videos after every live session is done, or yeah, you can just have a look at this video, and if you have skipped anything, you'll be able to watch the video here. Yeah, you can subscribe it here also if you want. um, right. So if a dog and cat, if the yeah, are you anyway linked with UNSW? I guess that's a out of the context question, but no, like I am linked with the UQ. So UQ is the University of Queensland uh, in Australia. UNSW is different. Okay. So like I guess like how many of you guys are like so if you want you can connect with me on LinkedIn actually. So I can share with you my profile. There you can like know where I'm like and what I'm doing. Okay. So I guess like the audience are same who were in the last class, or people are different this time. So please kind of like ping in the chat if you have attended the last class. You can just ping in the chat or like send some symbol or say yes if you are present in the last class that I took last week. Sumit was there, and who else? Meena Kumari was not there. Okay. So Meena, like, do you have any background on machine learning, or you are just starting it like everyone else? Okay, she is familiar with machine learning, I guess. So okay, so in today's session, like so last session, like people said they're not aware of machine learning much. So I gave a brief overview of machine learning, but in this class we will go through the assignments of week 1 and week 2 since they are released, and we'll try to solve them through and see what were the cases. Uh, okay, so the week 1 assignment solution is released. So we'll go through the week 1 assignment. So uh, okay. So have you guys like solved all this assignment? Okay. Okay. No response as yet. So what I'll do is that I'll go through the week one assignment and try to like tell like what it is and try to explain the solution, so that like if people are coming after this session is over, they will be able to look into the solutions as well. The question one is which of the following library to use NVIDIA GPU which of the following is a library to use NVIDIA GPU? So basically, NVIDIA is a GPU company which manufactures GPU, and to interact with the GPU, we need a language, right? So to perform operations on the GPU and perform certain maths, we need language. And PyTorch is a library actually. So here PyTorch is there. So it said PyTorch. PyTorch is a like actually a language. So let me download this it and put it in somewhere. How do I insert? Uh, download. Okay. So yeah. So this PyTorch, right? So PyTorch is kind of a deep learning library. So PyTorch is a deep learning library, and you can have different ML models in this library, and TensorFlow is the similar DL library. And PyTorch is built by Facebook, which is now Meta, and DL is this TensorFlow is built by Google, and these both are deep learning library. If you don't know, just it's just information. If you know, it's fine. Then CUDA is built by NVIDIA. CUDA is built by NVIDIA to sort of interact with the NVIDIA GPUs. So the correct answer is B here. And coming to the second question. Second question is which of the following is R a structural texture metric? So we know that the texture is of two type. One is structural and the second one is statistical. Okay. And co-occurrence matrix and local binary patterns are part of structural metric, and the Fourier coefficient and orientation histogram are part of statistical metrics, and you can find this information in lecture 1 or 0, I guess, of week 1. It's just a classification. I don't need to worry about much of that. Okay. Which among the following is a wavelet? So if you start to plot all these things, I'll just start plotting. So if you go about and plot the A, so suppose this is the wavelet, like this is 1, this is 2, this is 3, this is 4, this is 5, and this is 6. So if you plot the first one, the wavelet will be 1, then 4, then 6, then 4, then 1. So this is not the wave actually. And if you plot the second one will be the option B. So we have a -1 component here. We have -1 component here. So I'll put down on this -1, -2, and here is 1 and 2. So it will be like -1, then -2, then 0, then 2, then 1. So this is clearly not a like wave, you can say. Then the C, option C. Option C is like just you can just plot it and see, right? It has -1, 1, 2, and this is 0. So if you plot the option C, it will be like -1, 0, 2, and again -1. So this doesn't look like the wavelet. Let's plot the final one, which is the answer, I guess. The fourth one is it goes like -1, 2, 0, -2, -1, -1, 2, and 0, -2, 2, -1. So if you see, this looks like a wave. So that's why like option D, -1, 2, 0, -2, 1 imitates the wavelet. So that's why option D is the answer. So all this material, all these um, assignments that we're solving, it was from the week 1 actually. Since the assignment has been released, we are solving it in the class. Coming to the question 4. So if anyone wants to like ask doubts like while solving, they can like ping me. So I guess question 1 and 2 was pretty straightforward. If you have doubt in question number 3, you can like ask now. Otherwise, I will move to the question number 4, where I will tell about the local binary patterns. What were these and everyone is clear till question number 3. So I'll move to the question number 4. So do you guys know about local binary patterns? Like, do you guys know about the local binary patterns? Or should I explain it? Okay, so I'll just explain for sake of everyone. Local binary patterns. Local binary patterns. What local binary pattern says is that suppose this is the image and you picked a small region here, and that region is like having value like this. 5, 4, 2, 3, 7, 6, 9, 8, 1. So what you will do is that you will take this the center element 5. Okay. You will take the center element 5 and you will compare it with everything. So you compare it with 5. If it is less than 4, then you denote it as 0. 5 is less than, not less than, it's greater than. It's greater than 4, it will be 0, sorry, 1. If 5 is greater than 2, it will be 1 again. 5 is greater than 3, it will be 1 again. 5 is less than 7, it will be 0. 5 is less than 6, it will be 0. 5 is less than 9, it will be 0. 5 is less than 8, it will be 0. Like we are going clockwise. Okay. And 5 is greater than 1, it is 1. Okay. So just arrange all these digits 1, 1, 1, 0, 0, 0, 0, 1. And then you start rotating it till you get the number which has the highest value. So if you rotate this, it will be 1, 1, 1, 1, 0, 0, 0, 0. If you rotate once again, it will be 0, 1, 1, 1, 1. Like what you are rotating, just putting this thing here. Okay. So it will be 0, 1, 1, 1, 1, and again 3, 0. So you just keep rotating this, and the last element will be, I guess, like here, just a left shift from here. The last element will be 1, 1, 0, 0, 0, 0, 1, 1. So if you mark correctly, so this is the element with highest value, because all the ones are in the leftmost side, and we know that if numbers with higher value are in the leftmost side, it will have higher value. And the LBP value for this is like 8, right? So it is 127, then 64, 127 plus 64, plus this is 32 plus 16, the value will be the LBP of this. Similarly, in the question, so I'll just solve this one. So let's go by binary to decimal. 1, 1, 1, 1, 0, 0, 0, 0, 0, convert is 240. So if you convert this binary number to decimal number, it will be 240. And it is decimal. Okay. So this is like the way we calculate the local binary pattern of a pixel in an image. So similarly, if I go here and do the exact same thing for this, I guess, so if you look into 5 and you look into 5, the 5 has yes, the 5 is greater than 3, so it will be, yes, 1. Yes, 1. And 5 is greater than 4, it is 1. 5 is greater than 6, and less than 6, it will be 0. 5 is greater than 3, 1. 5 is less than 9, 0. 5 is less than 7, 0. 5 is greater than 1, 1. 5 is greater than 1, 1. And if you start rotating it, I guess, yeah, you just start rotating it. So the next rotation will be 1, 1, 1, 0, 1, 0, 0, and you keep on rotating it till you get to the last value, and you find the minimum of that, and you will get that that value is this one. The answer is C, right? So it will be 11. So it's just a task for you. Just go and see if, I guess, yeah, so this won't be, yeah, so yeah, so just a task for you. Just go and uh, find the smallest value while rotating this 5. So if you're not able to find, you can always check the solution that is there. So every course is provided with solutions. I guess you can just go to the solutions and see how solution is working. Okay. So this fourth problem is clear, right? Okay. Then the fifth. So I guess I uh, said something incorrect in the fourth problem. I guess it will be the opposite. It's not the same. Let me rewrite it again. So it will be opposite. Like if 5 is greater than this one, the result will be 0, other it will be false. So if I redo it again, so 5 is greater than 3, it will be 0. 5 is greater than 4, it will be 0, 0. 5 is greater than 6, less than 6, it will be 1. 5 is greater than 3, it will be 0. 5 is greater less than 9, it will be 1. 5 is greater than 5 is less than 7, it will be 1. Then this 2 will be 0, 0. So if you rotate this, I guess the smallest value it can go is when all the ones will be like this. So I guess after a few steps, you'll get something like these two ones will come here. So like just rotate it twice. I guess I'll rotate it twice. In fast rotation, you will get 0, 0, 0, 1, 0, 1, 1, 0. In the next rotation, you will get this 0 is coming here. Just put this 0 again here. So 0, 0, 0, 0, 1, 0, 1, 1. So this will be the smallest one among all the. So if you can go on and rotate it again and again, but I guess this will be the smallest one to see. Hence, its value is 11. Hence, the answer is C, 11. Okay, so this part is come. The Gabor wavelet is made up of two parts, which are it is Gaussian and sinusoidal. It's a direct question and answer. So I wouldn't go depth into it because it will be too much discussion for just one question. Okay, so in the sixth question is from the neural network. So what I will do is now is that I will start with the neural network part. Okay, and since I stopped last class with the neural network, saying that I will be teaching neural network this class. So I will be starting with neural network now. Joined. Ramesh Rao. Okay, so I'll be starting with neural networks now. So, so after that, we will solve all those problems. Okay. I have a doubt in question 2. Question 2 is which of the following is a structural matrix? So this is like not it's just information, like you cannot
Sir, may I call?
yes,
Hello.
yes.
Sir, in the presentation, it is given that texture in structure is LBP, Fourier coefficient, and wavelets. And in staticals is scope occurrence and orientation histogram. Sir, second number slide, second lecture, feature expression for visual computing.
Okay. So the answer is
I think answer is either
okay,
answer is wrong or there is some doubt in lecture slides in some.
let me see.
Slide number 5.
No, I made some notes, I guess. Okay, this one, right?
Yes.
Statistical is co-occurrence matrix and orientation histogram. Statistical is
And
orient.
that option is not given in that.
Acha, I see. Thank you. Actually, I also like thought this must be the answer. I couldn't like recall what was that. The structural should be the structural should be local binary patterns and the
Fourier coefficient.
coefficient. So double I and third I guess.
Yes.
And co-occurrence matrices are like, yeah, the statistical ones. Okay, I guess they should, the options would have been like not 1 and 2, it should be 3 and 2, I guess. 3 and 2.
Second and third is not given in that.
Yes, yes, 3 and the correct answer should be 3 and 2, but they haven't given. Um, Thank you. So, okay, so we'll be starting with neural networks. So basically, this will be the part. So this will be covering the some end part of week 1 and the entire week 2. So we'll try to cover everything. Just stay with me. If you have like any doubt, just unmute and ask. If you like do not have any background, I'll go very slow. So after the Sasi is asking, so are neural are like functions? Yes, like I will tell. So I will. So now it's like 6:30. I will teach till 7 and ask you guys like if this is going too fast or too slow, then you can like recommend me going slow or fast. Okay. So let's just start with neural networks. So last class we saw that in the ML we were given the XY pairs, and so there is some underlying function that relates between X and Y. So our work is to approximate this function F. Okay, approximate this function F means given AX, we will be able to say what will be the FX, or we will be able to approximately say what will be the FX, which is we can also notationally say Y. Okay, this one is clear, right? So last class I told that this X will be fed to a ML algorithm. Okay, and you will get Y. So in this class we'll look about like what is this ML algorithm, right? So what is this ML algorithm? So till now we don't know, like, it's just a black box for us. So we'll now uncover what is this ML algorithm is. And I got a question, like Sasi, if you want to ask question, just ask in the everyone's DM. So you're just directly sending me questions, I guess. This because like everyone can see the question and also they might want to participate. Also, you can unmute and say, okay. Okay, so starting with, so I'll go to Relu and all those things, but I'll start with basic nuance. Okay, so let's say your X is of two-dimensional, X1 and X2. Okay, so you want to, and you have like all these pairs, like you have a data set where uh, of I variables, uh, where I is ranging from 1 to M. Okay, so this data can be anything, like you can have so last class we saw that this can be your distance of your house to the medical, and this can be the distance of a house to the church, and you are given the distance to the medical and distance to the, let's say, school. We're kind of predicting what should be the price of the house. Okay, so this can be anything, right? And so you want to approximate this function. Okay, but you don't know what the function is, right? So I'll just go to the slides that I created last class just to like remind you that what this function was. Okay, otherwise you might be feeling lost. So this was the function, remember, like everyone can remember like this, right? So we saw that like if 2 is given and equivalent is 6, 3 is given equivalent is 11, 5 is given equivalent 27. So here fx is x square plus 2. So you're basically looking into these pairs of things, and you are predicting that, okay, this function is x square plus 2. But if the pattern is very, like, very vague, okay, like the pattern is very vague and it's very tough to predict. It's very like the function is very complex. It will be very tough for us to predict what function is this. So what we are doing, so just look into this carefully. This will change everything. So you don't know the function, right? So you can say, okay, I don't know the function. What I can do is that I can assume that my function is of some w into my this input x. Okay, I'll use a different color for that. Is some w. Okay, then into x plus b. Okay. So this, so example of this kind of function is 3x plus 2, 4x plus 5. Here w is 3 and b, w is 3 and w is 4. Here b is 2 and here b is 5. So this is okay. So let's start with a simpler one. So let's say you have only one x. Okay. Should I see w as slope and b as intercept? Yes, you can see that. You can frame it in that way. So we are basically solving this one. Okay. And let me just, move number. Okay, fine. So yes. So this is the function. We are assuming that, let's say the function is like this. So you have given a x and you have given a y, and you wanted to find the function that takes in x and gives y. So what you did in the step one, you sort of assumed that um, the function is kind of is a multiplication of your input text with some w that you don't know, and you add that with some bias that you don't know. So the task for us now will be to find this w and find this b instead of find the function, right? So Sasi asked one question: should I see w as slope and y as b? So if you look carefully, this is the equation of line, right? If you look carefully, this is the equation of line. And if you take x and so suppose this is b and w is the slope, so this will be wx plus b. Okay, so this is the this is the input, this is the x, this is the slope m. Okay, yes, it is a line. So do you see a problem with this method? Like if we, let's say we assume that the function is wx plus b, and so wherever I put a red mark, matlab, like we don't know that. Okay, so here w is written in red and b is written in red. So we can assume that we don't know w and b, but for some w and b, I can say my function is this. So what is the problem with this? Like, can anyone tell, like, what is the problem with this? If I just assume that my function will be is a form of this wx plus b. Anyone in the chat? Suppose Okay, Sasi is saying that how can we predict if you don't know the values? Okay, so you don't know value of W1B. So for now, I am assuming that I know the value of W1B. Okay, even if I know, so what is the problem with this method? Like for so given X and Y pairs, what is the problem of with this method to predict the function f? We don't know about the significance of parameter X. Okay, so I'll just try to simplify it and I'll just tell the answers to everyone. So a function can be anything, right? So we don't know the function. Like just suppose if you know a famous data set MNIST. So MNIST is a famous data set. MNIST. So here you'll be given the images of digits. Okay, one, and you'll be able to the level will be one. You'll be given the image of five. The level will be five. Okay. So if this is my X and this is my Y, the problem is that the function that take X and gives out Y, or so this is like a very tough example. But let's say you are given weights and you have to predict the age. Okay, the weight is 70, age is 21. If the weight is 90, let's say the age is 35, or age or anything. So what is the problem with this? That so some things can be linear, right? So the weight, the function of weight to age can be linear. Like you can say that not weight and age. I can say so. I can say experience, or we can say you can say uh, you can say the I power, then the age. Okay. So if the I power is 5, let's say 5, the age is 20. If the I power is 15, the age is 10. If the I power is let's say 0, let the age is 40. Okay. So you can see that the change is linear, right? 0, it is 40, and with, so this is suppose age, and this is suppose I power. With age, the I power is reducing. Okay. So if you put a line, it will be linear. Okay. Okay. And if you are given this X and Y pair, so this is X and this is Y, and you have to predict the function that relates between I power and S. And if you assume that this function is Wx plus B, and somehow you get, so I will tell how to get W and B. If somehow you get the values of W and B, you will be able to predict this function. Okay. You'll be able to correctly predict this function because the underlying function that we're trying to predict is linear. I mean, you can say that the I power is decreasing linearly with age. Okay, if the age increases, the I power reduces. So this is a direct correlation between these two things. But if I take some pairs, so suppose let's say this one, it is the image of 1 and you are predicting it as 1, it's image of 5 and predicting image as a 5. So if you try to like this is like image, so and this is like labels. Okay, if you try to plot a graph, it won't be this nice linear. Sorry, just use a red color for it. So it won't be this nice linear. It won't be. What it will be? It will be something, some non-linear. Okay, or it can be this or anything non-linear. The problem with this method is that this is the problem with this method is that it is linear. Okay, this is linear. Okay, so we need to add some sort of non-linearity to it such that this will be able to predict the non-linear functions that are there. This non-linear function that are there. I won't go into much of the math. You can go look into the lecture, and I'll just give you a flavor of what these things are, so you can, so that you can, if you don't, even if you don't understand the lectures, you can go again and watch and able to understand these lectures. Free like Wednesday or Thursday for same timing. If you are free on Wednesday, Thursday, then I'll be requested to NPTEL forum to make respective alternatives. I might leave at 7 because of another session scheduled. Okay. So actually, I mailed them like I mailed them to change the timing from 6 to 8 to 4 to 6 actually, or 5 to 7, such that people can attend this session and go to other session on Friday itself. If you want a different session on Thursday, Thursday can be possible, but Wednesday will not be possible, because Wednesday I have some other commitments. I guess I need to attend to that as well. So, okay, Wednesday also we can try, but Thursday and Friday is most preferable. Let's see. Okay, let's see what can be done. So, Friday 4 to 6 is good. Okay. So I'll try to stick to the Friday timing if time permits. Okay, so where were we? For me, 4 to 6 is busy. 5 to 7, we can do if you want. Mm. Okay. You can always watch recorded lectures, or the recorded version of this will be uploaded to YouTube. 5 to 6 is not possible. Okay. 6 to 8 is, I guess, a better timing, but I will see like if this can be moved to Thursday. I think everyone will be appreciate that, because Thursday 6 to 8 everyone is free, right? At least everyone who are in the chat, I guess. 6 to 8 is okay, but Thursday or Friday I can have to request on that. Okay. Is this because I'll try to request uh, to them to like change it to Thursday. So I'll just do the request. So see, I'll do the request today. So if they were able to change, it's better. Then you all will be fine. But otherwise, we can also can you also can like join here and after some time watch the recordings. Okay. So this thing is so coming to this discussion. So this is some function can be non-linear, so it's wiser to like make this assumption non-linear instead of making it linear. Okay, so I'll rewrite the function that we're trying to predict. So the function will be some non-linearity. I am denoting it as sigma, w into x plus p. So this can be any non-linearity. So there are a couple of options for non-linearity. One is softmax, one is ReLU, and another is TNS. So another is sigmoid. So there are different type of non-linearity. Okay. So this thing is clear, right? So we want to suppose there are some things which are non-linear in nature. To tackle these things, we're adding an extra layer of non-linearity on top of the linear function that you assumed. And I just reiterate this W and B we don't know. Okay. So I'm assuming that I know W and B. Given that I know W and B somehow, okay. So this can be a function, okay. So if so, this is like A and I power, and this is like digit image and the correct prediction for the level. So let's say I'm like I'll say that suppose this function is sin x, okay. So function is sin x. So its xy pair will be given x is 90-degree, sin x is 1, 0, and x is 0, something like that. I forgot the x. Okay. So for at 180, it's again 0, and for sin 30 is half, right? So these are the values, okay? So you might ask like, how can I represent sin x in terms of this? It's not possible, right? It's not possible to write sin x in terms of this. But remember what I'm saying, ML is a way to approximate function, not approximate function, like not exact. It's not an exact representation, it's an approximation. So, so there are proofs also. So they say that if you assume, uh, so, so they say that you can actually represent sin x as a approximation of this soft max of wx plus b. So this is the approximation of this. So sin x, softmax of wx plus b is the approximation of x, but the proper w and proper b need to be learned. Similarly, cos x will also can be represented using this wx plus b, but here the w and b will be different than this w and b. Okay, so the changing w and b, we can represent the same function using softmax, like using a non-linearity on top of this. So there are different type of non-linearity. One is softmax, one is ReLU, one is tannist, and one is sigmoid. There are others also. So these are called activation functions. In terms of neural networks, I will go into this once I go detail into all these stuffs. Okay. So the story so far is that not all XY pairs have an underlying linear function. Some have non-linear. So we want to not learn all we want to learn all those non-linear functions, or we want to approximate all those non-linear functions. So what we can do is that we can start with assuming that function. So first assumption is that the function is wx plus b, where w is the slope of the line and b is the bias. Then we can go about like, okay, so this is linear, let's just add a layer of non-linearity to it. So once we add a layer of non-linearity, so now the task is that, okay, we attach this non-linearity to wx plus b. Now the task is that find a w and find a b such that this entire thing will represent sin x, or the underlying function that we are trying to like predict. Okay, so this thing is clear, right? So if you're not clear, you can just stop me and like ask me to reiterate again. I can go again, but yeah, I guess hopefully this is clear till now. Okay, so let's just represent the same thing in using neural network. So I'll just try to do a neuron here. This is x, this is w, this is wx. Then I'm adding a b here. So this is wx plus b. Then I'm adding a non-linearity here. Non-linearity is like defined using like shown using this. This is sigma wx plus b. And we call this z. z, and so that's why this can also be looked like z. Okay, so this is x, this is basically x, not here, here, x. And this thing is called y. So is this diagram clear? Like this is neural network. Is this diagram clear? Like this is like this x can be anything. This x can be a picture of cat. This x can be a text. This x can be any music. This x can be any geographical location. This x can be a digit x7 or anything. This x can be anything. So I'll just multiply it with the w. I'll just add a bias b. Then I'll add a layer of non-linearity and get my y. So this whole process, this entire process is sort of kind of trying to the function fx that relates to this xy pair. Okay. So is this problem statement clear to you all? Hello. So can anyone like clarify it in the chat? Yes. Meena. It is. Anyone else? Okay. So I'll just move forward. I'll assume that everyone is clear on this. And Sumit and Sasi, if you guys are not clear, like you can ping me now. I can go again. Okay. So moving forward, like how to learn this W and B. Uh, so how to know relationship between X and Y, like when there are thousands of items. Is it plotting between X and Y? So this question. Okay. So good question. So the relationship between X and Y is not known. Okay. So I'll just try to do the same, like say that same thing that I mentioned earlier. Suppose you have cat image and it's labeled as cat, and dog image and it's labeled as dog. So how would you like how do you like to so how do you define the relationship between dog and its labeled dog? You cannot plot these things, right? Because these are very high dimensional. It's not like that x is just a number. So I just told you, right? X can be anything. It can be image, a text, a wave sound, a IP address, or a geographical location, or a number. But everything can be represented as a number. It's uh, as a number, but we cannot plot them. Here we can use features of image. Yes, the features of image we can use, but how do we know the relation between the features of image and the label? So in case of like the way said, like this relationship is learned by the machine learning algorithm. Okay, so the ML algorithm learns this relationship between X and Y and try to give you. So this underlying function that is there, this is the like this function is the underlying relationship between X and Y. So we don't know this function. Okay, what do we have? We just have X, Y, and pairs. We're trying to learn the relationship between X and Y, or you can say we're trying to learn this function, or we're trying to approximate this function given X and Y pairs. How we are approximating? We're we're assuming that we don't know anything about f, so we're just saying that f is fx is something like wx plus b. We assume that this is the case, and for non-linearity, we're adding a non-linear layer on top of that. So this is just a pictorial representation of the same thing that I said. Okay, so how to know the relationship between this? We'll just assume this, then we'll try to find this w and b, and then we are able to, then we are good to go. Then we can say that, okay, for a given w and b, this thing correctly or maximally approximate our the underlying function which describe this x and y. So once we find the correct w and b, then what we can do, like given a test x, okay, test x, we can just multiply it with w, add b, add the nonlinearity, and find the label. So this text x can be anything, like, so you trained your images using bunch of cat and dog images. Now you have a new cat images and you want to predict if it is a cat or dog. So as human, you can always do, like, you can just look at it and say that it's a cat or dog. But as a machine, so this need to like take that cat image, multiply it with the weight, then add this bias, and then put a non-linear layer on top of it, and the value it got, so it will say that, okay, this level is cat or this level is dog. So as humans, we have this like cognition that, okay, this is cat and dog, but internally, so this cat image and cat label has a relationship that we don't know. We just approximated the relationship using this, and so after this approximation is done, we'll have the correct set of w and b which correctly classify this as a cat or a dog. Okay, so I guess it's clear now, right? Then we can move to how to learn this w and b. Okay, so I guess everyone is clear. Now the time is 7:07. You can just now, like, everyone, Meena and Sumit or Sasi, anyone out of you can just tell me, like, if I'm going too fast or too slow, or it is fine. Okay, it's fine. So how to learn these weights? So I'll come to something called gradient descent. Okay. Okay, so let me before coming to gradient descent, let me just tell you about types of classification. Blue. The classification can be like binary or multi-class. Okay, so if the classification is binary, so we have only two classes. In multi-class, we have many classes. Let's say k. Okay, in two class we can denote it as class 0, class 1. In multi-class, we can just go class 0, class 1 up to class k. So this is just terminology. So for a cat dog classification, it's a type of binary classification. So we can just so when you're passing something to machine, it obviously cannot understand text. So you have to assign some labels to the labels. Okay, so we can say cat is 0 and dog is 1. Okay, so given this, okay, given this, suppose I have a dog image. Okay, x. So I have a dog image. It's not a dog, but assume that's a dog. So this is the x. Okay, this is the x, and I'm denoting it as a one neuron, but this will be many neurons. But just to represent, I'll just represent it as one neuron, and I will just so I don't know w and b, right? So what can I do? I can just randomly initialize w. So we want to learn. So now the problem is that we want to find relations between x and y's, but we only have so w sorry x and y, and we have to find the underlying function out of it. So now this underlying function is like the task is reduced set. We need to find this W and B, which can correctly define or correctly approximate our function. So let's say that so this is W. We multiplied it with W and we got Wx. We added this by B. We got Z, which is Wx plus B. We added a layer of nonlinearity here, and we got sigma of Z, and this is my Y. Okay. So this sigma is called activation function. So what? So one example of sigma is sigmoid, and its extended version is softmax. Let's focus on sigmoid. Okay, sigmoid is 1 by 1 plus e to the power minus x. So this will be 1 by 1 plus e to the power minus z, or which will be equivalent to 1 by 1 plus e to the power minus Wx plus b. Okay. One interesting property of this function, it's just a function, okay, sigmoid function. So don't think about it. One interesting property of this function is that sigma z, I mean this quantity, the final quantity, will always be between 0 to 1. Okay. It will always be between 0 to 1. So what we can now think that, so this is y, right? So sigma z is y itself. Okay. Now you can think that suppose an image is given. So and suppose we got the y as 0.91, or one image is given, we got it for 0.31, 0.42. So this we will get. So suppose this we got for dog, this we got for cat, this we again got for cat. Okay. But what their actual level? Dog's actual value is 1, cat's actual value is 0, this cat's actual value is 0, right? We stated that cat is 0 and dog is 1. So how do we like plan, like how do we plan this? How do we denote this as dog? So one way is that we can say that if my sigma of z is greater than a threshold t, I can put it as dog, else cat, right? This is one way. So what is the ideal way to set the threshold? 0.5. Okay. So we can say that, so this gives me a probability of a image being a cat or dog. If the probability is more than 5, it's a dog. The probability is less than 5, it's a cat. I guess it's clear, right? Like, so every time you pass a image, so every time you give this network a image, it will give you a score between 0 to 1, close bracket. Sorry, open bracket, 0 to 1. Okay, and you can just take this score and check if greater than 5, 0.5. If it is 5, then it is a dog, and if less than 0.5, it's a cat, right? So this is done. Okay, so but this is the like entire the network the flow, right? But how do we get the W and B? So what we can do, so I'll just start writing the steps of gradient descent. Gradient descent. So step 1 is randomly initialize W and P. Okay, step 1. So this is simple, like we can just randomly initialize W and B. Second is do a forward pass. What's a forward pass? So I'll just explain. Forward pass is same as given a x. So this will be can be image of cat or something. You just calculate x into w plus b. Then you append a plus b, which is z, and you get y. So this is the forward pass. Okay. This is a forward pass. I mean, just take the input, multiply it as w and b, and add b, then add the nonlinearity and get the y. This is the forward pass. So suppose let's say this is an image of dog, okay, and so this image of dog, and you passed the image of dog till the last point, and you got 0.1, okay. But so tell me, so we're doing it correctly or incorrectly? Just tell in the chat, because we want the final score to be more than 0.5 to be a dog, right? But we're getting a score of 0.1. Okay. So are we in the right direction or we're missing something? Just tell in the chat or like unmute and tell. I guess the interaction should be there. Okay. Sumit is asking which activation function is used, how is it decided? So currently I am using softmax. Okay. Or you can say sigmoid I am using. But what others are there, I listed it here. When to use what, I will tell it later. But as of now, for binary classification, you can just go with sigmoid because it squeezes the value between 0 to 1, and you need probability at the end. So since you need probability at the end, so you can, so at the end layer, you have to put, yes, someone is speaking. Since okay, so since we need probability score at the end, so we need something between 0 and 1, so we put sigmoid as at the end layer, but others I will tell about it. But yes, for binary classification we always use sigmoid because it gives the value between 0 to 1. If you see, if you plot sigmoid, so it's like this. So this is 1 and this is half actually. Sorry, yes, at 0, thus okay, so I'll just okay. So this is the plot for sigmoid, okay. This is 1 and this is half. So since I told here this is the function for sigmoid, if you put 0 here, you put if you put 0 as z, so it will be 1 by 1 plus e to the power minus 0, 1 by 1 plus 1 half. This is half. In the when the x is 0, the sigmoid is half. Then when the x goes to infinity, it touches 1. When the x goes to negative infinity, it touches 0. It is never 0, but it touches 0, sort of. So what is wrong here? Like, so my coming back to my question, what is wrong here? Like, we wanted to classify the images of dog and cat, and we make a forward pass. Given an image of dog, we got a score of 0.1. But we should be getting a score closer to closer to 1, because I said that dog is level 1. So we should be getting some score like 0.9 or 0.8, or you can say more than 0.5. But clearly we are getting negatives, like a very bad score here. So who could be the culprit among this? So X cannot be the culprit, right? Because X is the input. How can you like make this as clear culprit? So here X cannot be culprit. This sigma cannot be culprit because it is a sigmoid. It is just pressing the value between 0.1 to 1. So the culprit can be W and B, right? So we need to punish W and B, not others. Okay. So moving forward with it. So the third step here is, so moving forward, the third step is calculate the error, or or how much we missed. Okay. So the dog, so the dog should be, value for dog should be 1, but how, what did we get? We get 0.1. So how much we miss? 0.9. Okay, it's clear. Like I just subtracted it. You can say, you can take a LP norm of it, L2 or L3, anything, L2 or L1, any norm. But I just did a direct subtraction for the simplicity. So how much we missed? We missed by 0.9. So what should be our task? Our task is that we should find that W and B which will minimize this one. Is this thing clear? Calculate error. So error here will be y minus y hat. So let's say this is y hat. So y, let's say this is y hat. Okay. So how much did we miss? This much. Y minus y hat, or I can say loss between y and y hat. Okay. So this is called the loss. Okay, the loss. I mean, the what is the loss we have? So we first we randomly initialize W and B. We do a forward pass. We got a value 0.1. The loss is 0.9. Or you can say, how much did we miss by 0.9? Okay. Till step 3, everything is clear, right? So we're calculating loss and we're giving this error value. Okay. So given this loss error value, so what we need to do is that we need to find W and B that minimizes the loss or cost. This is also called cost. Okay. So then I'll try to like write it again. So I can say the J of, so I'm denoting loss as J. Okay. And the J is my actual Y. So actual Y is dog 1 minus the Y I predicted with my forward pass. This can again be rewritten as Y minus Y hat is sigma Z. Then you can say Y minus sigma Z can again written as Wx plus P, can be Y minus the sigma of this is 1 by 1 plus e to the power minus Wx plus B. Okay. Hence, my loss is Y minus 1 by 1 plus e to the power minus Wx plus B. So this is kind of a mathematical formula where the loss is defined like this. So I will not like go depth into it. So you can just again always look into the lectures for the details. But I can say that so this is pretty much everything. And so we can say J is a function of X now, right? And if I plot this, this is X and this is J. I can just like plot like, okay, so this can be the Jx. Okay. So this is a plot between X and Jx, not between X and Y or X or Fx. It is between X and the loss. Okay. So everyone is clear till this point, right? So just let me know in the chat. So I'll just reiterate what I said. we initialize randomly W and B. We did a forward pass. So we got the 0.1. We found the error, and I just expanded this y minus y hat till this point, and I sort of plotted this g of x or y minus y hat like this. Let's say this looks like this, and this is x. So what is our goal? So our goal is that okay. So I'll just read through this. So okay. Okay, so I replaced x with w. So no one should have a problem with this because z is a function of w. X, I agree. Also a function of w because anything like if I change w here, if I change different w here, you will get different value for z. So what I did is that I just took different value for w and plotted this against a different value of zw. Okay, so this is the thing. Okay, so let's assume that we don't have a b. Okay, we don't have a b. Let's assume that we don't have a b. So then next I will like say, what if we have a b? Okay, let's assume that we don't have a b. So remember what was our goal? So our goal was to find the function which correctly approximate the underlying true function. Okay, and then we kind of refreshed the problem that find the w and b which gives a correct approximation of the function, or we can say that find a w and b which gives lower error, or I can say find a w and b which minimizes the error between y and y dash, this one, which minimizes this one. Okay, or I can say find a w and b which will give me minimum error when an image is passed. So this formulation you just note it down in your notebook so that you won't be confused. What is the goal that we are trying to track? Okay, since now we have deleted b, we are like looking into something that give me only a w. So let's say I know b has somehow give me just only a w which will give me minimum error. Okay, so if a kid is asked like what is the point where this error is minimum, here they can easily tell that this is the point, right? Is everyone agreeing with me? This is the point where the error will be minimum, right? This is the point. Let's say this is wi. Say this. Let's say w solution, right? ws. Okay, everyone is agreeing with me, right? Till that point. So then I will proceed because this is the main part. This explains the entire deep learning or entire computer vision, everything. So if you are not clear here, you won't be able to like proceed further. If you're not clear, I will just reiterate things, but like, give me a sign in the chat. Okay. Mean yes. Submit is yes, sir. Okay. Uh, okay. But just try to recall the step one. What was the step one? The step one is randomly initialize W and B. So it's a random initialization. We can say that, let's say the random initialization W is here. Wi. Okay. So now the problem reduces that how to bring this W down to here, right? So I'll just let you know, like I'll just do one thing, you will be convinced, I guess. So what I can do is that take a slope, find the slope of JW. Okay. So I'll just write the steps. First is find slope of JW at Wi. I can just find a slope here, right? So this is the slope. the slope will be positive in this direction. Okay. Second, take a step in the opposite direction of slope. Okay. And third is that repeat till convergence. So first we find the slope. So this slope will be positive. Okay, but we'll take a step in the opposite direction. Okay, so this is the correct direction. We will take the opposite direction. How much we will take the step? So this you can like specify it as lambda, some small lambda. You can set it. You can set it by yourself. It's called hyperparameters. So these w and b are the parameters of the function. This lambda will be hyperparameters. It's called hyperparams. Okay. You set w and b. You sort of so you took a step in the opposite direction. You end up here. Okay. You repeat. You again find the slope here. It's again positive, and in that direction, you take another step in this direction. You reached here, and you take again a slope. You again came in this direction. You came here, and sort of continuing. You will be reaching near here. Okay. So by this step, you sort of reached here. Okay. So if I just write it in this way, so here will be wi plus 1 will be wi opposite direction negative lambda into. So how do you calculate the slope? The slope is calculated using the gradient. The gradient of jw, gradient of w with respect to jw. Okay, so this is the entire gradient descent algorithm. So how do you so this is the till you have to repeat this step till convergence. So initially you will have w1. After iteration 1 it will be w2. After iteration 3 it will be w3. You repeat this till the last point. You will have w, say, k or m. After this wm will be the w where the loss is minimum. The loss is minimum is the difference between y and y dash is minimum, and difference between y and y dash is minimum. Matlab, the function you are trying to approximate is near, and you can say so. After all these things is done, you pass the dog image, do a forward pass. So this is the this is like training is done. So you go here and you do the testing. You take a new dog image. You do the entire forward pass. You will see the score will always be greater than 0.5. It can be anything 0.7, 0.65, and but it will always be 0.5. Since you have learned that weight which minimizes this z, you'll always get something where the difference between y and y dash will be low. And since you increase the value more, you'll get less for dog, and decrease the value, we'll get less score for cat. For cat, you'll get a score will be less than 0.5. And the y minus y dash, y hat will again be less, very less. And so this is the entire like sort of gradient descent algorithm where you are finding this w repetitively, like subtracting it from the past w in the direction opposite to the gradient. So let's, or it also work in the opposite direction also, like if yeah, if sort of your initialized W somewhere here and you take a slope here, this slope is negative, right? So this is 0, this is negative, this is positive. So you'll, since this is negative, you'll take a step in this direction. It's like it is coming, like it's kind of dragging into this direction, and you'll go down, and you'll come finally here. Okay, this is the point of minima. Okay, is this thing clear? So let me know in the chat. This is the like most important thing. If this is clear, like everything else will be clear from this point of time. Sumit said yes. Everyone else do the same. Let me know everyone else. Meena said yes. Sasi, Ramaneshu, Ramesh Rahu. So this thing is clear. So I'll just like go very fast now because I guess this thing is clear. So what happened to B? What happened to B? So we also don't know B, right? So we just assume that we know B. So for B, we can just do a similar setting, right? So we can just do a 3D thing where the function is like this. Okay, and this is J, WB, and this is B, and this is W. So you are sort of finding correct set of B and W which minimizes this, and you can just start at a random point where the W will be something and B will be something. Just move in this direction and you come here. And if you start from this direction, you'll go this direction, and you'll finally come here. Okay, this is pretty simple. Like, does this the same thing apply? If my W is n dimensional and my B is some k dimensional, the graph I cannot plot, but W and B will be also like similarly some m dimensional, and you have to plot that one dimensional graph to show that. And the curve will be similar like this, and you will again come to the down, come to the minimum point. Okay, so this is the entire thing. Okay, and this explains so this like when I said W is top dimension this, I can just design that. Okay, so suppose you are looking into a cat image, and here one neuron, so these are called neurons, so one neuron represent one pixel, p1, p2, and suppose you have an image of 28 cross 28, and it's a grayscale image, you'll get 756 total, 786, I guess. 28 cross 28, 784. So P784. So you have this. So you have so these are the weights. So weight dimension will be 784 cross 1, and you are adding a bias B. The bias dimension is r to the power 1, and you are getting a Z here. and then you are applying a non-linearity on Z, and you are getting Y hat. So this is a neural network. This is a one layer neural network where the inputs are pixels, and you are multiplying pixels with W, and you are adding then a bias, then you are getting Z. That Z is you are applying non-linear on Z, and you are getting a Y dash, right? And after getting Y dash, what you will do, you will calculate the error Y dash minus Y, and then you will sort of find the, like, using gradient descent, you will find, so this is W1, this is W1, W1, you'll then find W2 up to WK, and this WK, so after training this WK, when it will be multiplied with X and added with the correct B. So similarly also you'll find B1, B2 up to BK, and when you'll multiplying with W and adding with B and adding a non-linearity on top of it, you'll get a Y hat, which will be closely related to Y. This thing is clear, right? I mean, this the entire setting where we are passing the input and finding Y is clear, right? So one question, like, where do we stop? Like I said that repeat till convergence. So what is the point of convergence? So one point is that you can just set it as 100. Like I want to do this going down thing 100. Okay. So even if, like, so you might ask, like, what if we skip this part? We skip this part and go in this direction. So you cannot go in this direction, because like when you're coming from this, you'll go here, and when you come here, you will again come back, because in at this point the gradient will be in the opposite direction. You are moving in the opposite direction, so then you will come back here. uh, uh, so you'll always end up here. Okay. Okay, so also this thing is like, so till convergence is one is like you just I'm coming to you, Sumit, so just wait. Okay, so one is like you just said, okay, I'll just do it for 1,000 or 100 iterations. Second way of dealing with it is, I can say, I will so I will go till so there is not much change in the input. So if you look into this, you can look into this diagram, so when you're coming here, so here you will be moving very fast, because if you just take a step, you'll be like coming from here to here, right? But here, if you take a step, you'll be traveling very less distance. So this is like the distance you're traveling is less here, but in the vertical direction, you're traveling very much. So the change in W is much less than the change in JFW. JFW. Because if you move here also, the change in W is less, but the change in W is same, but the change in JW is like the way, like you are changing the JW is much more lesser. Like you're just coming from this point to this point, so the change will be very less. Here it's more, here it's quite more. You can say that when the change in J theta is kind of converging, or the change in J theta is very low, then we're sort of saying that we sort of reach the convergence, and we should stop training our neural network. And so this is a like example of basic neural network. Okay. And so these W and B are called the parameters, and the lambda that I defined here is lambda, or someone also can say it as alpha. Any symbol can be present. This is called the hyperparameter. So what is the number of parameters? Just if someone can tell, if this is the input is 784, and this is like 1. So the number of parameter I will just tell. So if since the input is 784, we need like input is 1 into 784. To multiply this, we need a matrix W of 784 cross 1. So there are 784 weights. And also we have a bias term B. So it's a number 1. So the total number of parameters we have is 784 plus 1 equals to 785. Okay. And this is not a parameter. And one hyperparameter is there. So this is the example of normal neural network, one layer neural network. So I'll just go into the terminologies before answering Sumit's question. So what if we attach? So people have seen that. So taking into one layer into account, and if we go deeper, like if I just design a neural network like this, and the second layer, I also added some more neurons. And again in the third layer, I have added one neuron. So here it will be connected like this, and here it will be connected like this. So here it is input X, it is W1, W2. You can entirely call this as W. You are passing this, so this is X. You are getting W and X. You are adding a bias here, plus B. Then you are again passing this, and even again W and X plus B into W2 plus B. So this is your X, Z now. So this is your Z now. This is okay. Hmm. So this is your this is Z now, and you pass the non-linearity here, and you get the what is happening. You get the y hat. Okay. So this is, so I'll just briefly tell about the terminology. This is the input layer. This is the hidden layer. This is the input layer. This is the output layer. So it's not a 3-layer neural network, it's a 2-layer neural network. So we don't count the input layer, it's layer 1, layer 2. Okay. So these are just terminologies, and you can like, so since now the dimension of W and B will be much larger, it's very hard to represent that, okay, in a graphical way. But you just like remember the intuition, you are just taking X and we're just multiplying it with some X, then we're again multiplying with some we're multiplying it with some W, then we're adding some bias. Also here we'll again add a non-linearity before passing it to the next layer. Then again we're like multiplying with some W and adding a sum bias, and we're just getting this sigma Z, and at the end we're getting y hat. So the question that Sumit Kumar asked is that, is function self always remain the same, ball self, for all type of linear problems or non-linear problems? So this is for linear. Okay, for linear problems, I guess the functions stays ball shaped, because for linear it will be ball shaped. For non-linear, it will be something, anything random, anything like this. So there, like if your initial W is here, you need to go till here. You may like, it is the local minima, and this are so local minima is a local or global minima. But if you are here, you can always reach till here. Because here is the global minima and here is the local minima. And we assume that local minima is the global minima in case of neural networks. since we cannot find the global minimum, it's still hard to find the global minimum, because suppose if the we have basically between JW and W, if the safe is like this and you are like this, you can never escape this minima, right? Because whenever you go here, in the next step, suppose you are in the step M, and in the step M plus 1, what we are doing, we're just finding the gradient of step, and we're traveling in the opposite direction, right? So if you are here, the gradient will be negative, and you will always travel in this direction, and you will reach here. Also, if you are here, you'll travel this direction, you will reach here. You can never skip this minima and come here actually. So if here is the actual minimum. Here is the minimum that you will find. Okay. So what is the like solution for this? The solution for is that you just go around and randomly initialize 3-4 times. Okay. So we assume that once you will reach here, sometime your initialization will be here, some date is here, but someday it might be here, and you will out of this 3-4 initialization, you will get one solution which will give you the lowest error. So you can just go with that W, okay, and cancel these two W's. So I guess last part was a very like a little faster, but I wanted to say that like this is the main idea. You can just rewatch the thing and try to fit this thing into you, like fit this concept into your mind, and we can just go around and solve the problems of week one now. So this covers like week one and week two some of the materials. So basically an image you can just pass it as a like collection of pixels here, pixel one number 1 to pixel number 748, and you will pass it to layer 1, and the layer 1 will be passed to layer 2, and this will give a y hat, and that y hat will be compared with a y, and we will get an error. For that error we will calculate the gradient, and using that gradient we will update all those weights. Okay, and for this we can update the weights. For this we have to back propagate the gradient error so that we can update these weights. So one is unmute. Okay, I have muted, and you can back propagate this, and you will get corresponding errors, so for corresponding updates here. And after doing it for certain iterations till convergence, you can actually get those set of weights and biases which will minimize this loss, or you can say which will correctly predict your images as dog or cat. Okay, so coming back to the questions that we have here, from question number 6, I guess. So this question says, how many learnable parameters does a zero bias neural networks with 30 input neurons, 15 hidden neurons, and 2 output neurons have? So let's just understand this question. I'll just so if anyone like want to like have solved, they can raise their hand, but I'll just do these things. Okay. So they are saying that 30 input neurons. So input neuron is 30. Okay. Is 130. Okay. And 15 hidden neurons. 15 hidden neurons and 2 output neurons. 2 output neurons. Okay. So if this is X and this is Y, so here Y is 2-dimensional. So I will discuss about 2-dimensional Y later. So we only learned about 1-dimensional Y, but 2-dimensional Y do present. And zero bias, no bias will be added here. Okay. So input will be 1 cross 30. Okay. And this weights will be, since the input is, so this is 13 neuron and this is 15, it will consist of a matrix 30 cross 15. Okay. Since it is 15 and it is 2, so it will be 15 cross 2 matrix. Okay. Okay. So someone is saying week 3 autoencoder program run. So error already. I sent question. Kindly like write the question correctly, that I can understand. So these inputs are not parameters. Parameters are this and this. So here 30 cross 15, it's the weights, and this is 15 cross 2, it is 30 number of weights since there are no biases. So this is 15 cross 3, 450, and if we add this, it will be 480. So the correct answer will be C here. C here. Right. I guess everyone is clear how this calculation was done. Okay. So question number 7. What is the range of sigmoid function for an input having a range 0 to infinity? So I'll just go to the plot that I mentioned here. In the plot, I mentioned that. Okay. In the plot, I mentioned that this is a sigmoid, right? Sigmoid is having a value half when the input is 0, and since when it goes to infinity, it touches 1. So the range will be 0.5 to 1. Okay. Come back to the question. Question number 7. The range of sigmoid function for an input having 0 at 0 point, at point 0 it is 0.5. At infinity it is 1. So the option will be D, 0.5 to 1. And 0.5 is included and 1 is not included. I mentioned that is open. So this can also be treated as this. Okay. Find co-occurrence matrix for this one. So this will take a while, co-occurrence matrix. So I'll just refer to the lecture number 1. So it's an easy one you can do. This will take time, so that's why I'm not doing it now. Right now, the time is about to over. Which features of a graphical processing unit makes it suitable for machine vision application? So GPU current. So when you look into CPU has cores which do serial jobs, but when you look into GPUs, so they do parallel computing. Okay. So what they are doing is that, so if you're calculating all this, multiplying all this, okay, where is it? So when you're multiplying all these weights with W, so weights with X, so X1 should be multiplied with W11 and X2 will be W12. So since we are multiplying so many things, you need parallel computing. You need all these things be multiplied with each other parallelly. So this parallel computing feature of GPU makes it better. The last question, which of the following is loss function? So one was so softmax and ReLU was activation function, and mean square error and cross entropy is the example of loss function. So I have talked about mean square error, or you can simple difference. I haven't talked about cross entropy. I'll talk about cross entropy in the next class. So answer will be A and D, so which is option A. Okay, so we have discussed all the questions of assignment 1. I guess some guest has asked, sir, week 3, one question not run. Program error is in 4. Is 4 IMD equals to this one. Image open driver unsupported operator unplot. If image file unplot. Okay, so this is the programming error. So we haven't done programming yet. Okay, so if you're attending these lectures like regularly, you can say that this programming we haven't done programming. We're still in the neural network phase. We will do the programming of neural network and some questions of it in the next class. Okay, but since week three videos has been released and you are doing the assignments, you can just post these questions in the discussion forum. By tomorrow or day after tomorrow, I will pick these questions up and I will try to resolve the error there itself. So for me, like, it will be easier to solve the errors there than like going through the errors now and like try to recreate it and reason it and try to give you a result. Okay, so is it clear? Like, so kindly ask in the discussion forum. I'll try to pick it up by tomorrow. Okay. Okay, so apart from that error message in the chat, so all these things that I discussed, is everything clear? Like, if someone like can give me a feedback on this, like if it is clear or not clear, should I go fast or should I go slow? Should I go in this space? Kindly everyone reply in the chat. I guess the time is over now. Okay. I'm going to thank you, sir, but it's from a number. I don't know who this is. 5275 30999. Sumit and Meena said this is clear. So we'll go deeper from the next class and we'll try to reach till week 3. Thank you for the session. So I will be uploading these things to my YouTube channel. So I guess they said that they will share all these things, all the seats and all the recordings with you. But unfortunately, I don't know why they haven't shared it with you. But you just go to the YouTube channel. So I shared the YouTube channel earlier in the chat. I can just go. Channel. If the number of players you are requiring is 5, then you can go for 10. So this is the channel, like one the past video. So this is the channel link. You can subscribe this and you will be getting notifications when I will add the video for this class session. So if you also like, if you know other people who took this course, you can just share these uh, recordings with them because I was thinking that they got this, they're getting this recording links, but unfortunately they're not. So you can also share this with others who want to learn about all these things, because since we're covering it sequentially, and of course we'll start with the coding part in the next class for the theory that I discussed in this class. So you can expect a coding session next week, and yeah, I guess this concludes the class, I mean the session. So bye bye, good night, bye. Thank you. By I'm ending the session. If you haven't subscribed or like see the thing, like you can do it right now. Just copy the link so that you'll be able to refer that. Okay. Bye. The channel name is Curated Tabs. Bye.